Hi, welcome to the lecture 4 of our series on data communication and computer networking. In our last lecture, we studied about the network core in detail. We studied about the circuit switching and packet switching, and then we studied in detail about forwarding and routing, and then the packet switching networks. Today, we'll move forward and study about different internet structures, and we'll study about the internet service providers in detail, and then we will study about packet delay and packet loss. Okay, so let's get started. Okay, suppose we have these end systems over here, this laptop, this mobile phone, this car, this smart fridge. So how do these connect into the internet? So how do they connect, or how do they transfer data, or how do they transmit data over this network? Let's suppose this end device over here, it wants to transmit data to this end device over here. So how do these end devices, which are present far away from each other, how do they communicate with each other over the internet? So how do these devices connect into the internet? So um, the answer is the ISPs. These end devices, they are connected to the internet using these ISPs. ISP means internet service provider. As we have already studied that the ISP, they itself are networks, and they're networks of interconnected routers and links. So we connect to the internet using or with the help of these ISPs. So hosts connect to the internet via access internet service providers. Access ISPs in turn must be interconnected. Of course, they needs to be interconnected as well. So in order for the packet to transmit from one end device to the other. So these ISPs must be interconnected so that any two hosts anywhere can send packets to each other. Then the resulting network of networks is very complex. So this evolution of networks is driven by economics and national policies. So let's take a stepwise approach to describe current internet structure. So suppose we have millions and billions of internet access points. Sorry, we have millions and billions of access networks. Suppose you are provided, you're using DSL. You're connected to the internet using the DSL. Your telephone company in this case is the ISP, or you might be using a cable-based internet, as we have studied about the internet, the residential access networks in a last lecture. We studied about the DSL internet access network in detail, and we studied about the cable-based access networks in pretty much detail in a last lecture. So suppose you are using a DSL. So in this case, your telephone company is your ISP. So suppose we have millions and billions of access networks today in this world. So as we have seen that these access networks, they must be interconnected with each other. So a packet can transmit from one source to the other. So here is a question for you. Given millions of access ISPs, the question is how to connect them together. So one simple approach might be to connect all of these access networks to each other. So one single access network, let's say this access network over here, this access network over here, it's connected to each of the other access networks in this world. I suppose it's connected to this one as well. It's connected to this access network as well. And the same access network is connected to this one. So this is connected to this one. This is connected to this access network over here, and this is connected to this access network over here. So one simple approach is to connect each of these access networks together. Let me remove this ink. So this approach is not a feasible approach, because in this case the cost of the communication links, of course we connect these access networks together with the help of the communication link. The communication link, we studied about the physical media in detail in our last lecture. So the communication links can be guided physical media, or we can have unguided physical media. So the costs of the communication links which connect all of these access networks with each other, the cost would be very, very high. So it's not a feasible solution. Okay, so you can see like this can be one approach. Each of these access networks is connected to the other access networks present in this world. So the connecting each access ISP to each other directly does not scale. So we would end up having order of n2 connections. So what can be the solution? The solution is to have a global or transit internet service provider. So each of these access networks, they're connected to the global ISPs instead of connecting to other access networks, or instead of connecting to each other, these access networks are connected to a global ISP. So one option is to connect each access ISP to one global transit ISP. So we have, in this case, we have a customer and provider relationship. So in this case, we have this access network. This access network, like all of these access networks, they are acting as customers. Let's denote it with C. So this global ISP, it's acting as a provider. So these customer access networks, they pay for the services they receive from these global ISPs. So these access networks, they pay to these global ISPs, the companies which are operating these global ISPs, for the services they receive from these global ISPs. So if we have only one single ISP, and which is providing services in turn for money, so it's a viable business. So of course we would end up having competitors in this business. So if one global ISP is a viable business, there will be, okay, so if one global ISP is a viable business, then of course there will be competitors. So let's suppose we have, in reality, we have dozens of global internet service providers. So, for your understanding, let's draw only three global ISPs over here. So we have different global ISPs. So each of these access networks are connected to one of these global ISPs. So these four ISPs are connected, sorry, these four access networks are connected to this global ISP, let's say ISP A. These access networks are connected to this ISP C, and these access networks are connected to this ISP B. So keep in mind, in order for a packet to transmit from one end device to the other over the network. So as we have seen that the internet service providers, the ISP networks must be interconnected. So in this case, these global ISPs must be interconnected as well. So we connect these ISPs together with the help of IXPs and peering. So with the help of internet exchange points, we connect these global ISPs together. So we have the peering links as well. With the help of the peering links and IXPs, we connect these global ISPs together. Then we have regional ISPs. In case of regional ISPs, the access networks are connected to regional ISPs, and then the regional ISPs are in turn connected to the global ISPs. So then comes the content provider network. So, for example, Google is a content provider network. Google, as of 2021, Google had 30 to 50 data centers, each having hundreds of thousands of servers, and some of the data centers have maybe hundreds of the servers. So these content provider networks, such as Google, they may run their own private networks to bring services and content close to end users. So in this case, these content provider networks, they bypass these global internet service providers. So content provider network, they bypass this global ISPs, and they connect directly, or they provide services or the content directly to the end users. Okay, so let's understand the structure using this diagram over here. So we have these global ISPs. We call them tier 1 ISPs. So we at the tier 1 we have these global ISPs, and then the global sorry the content provider networks. Let's say in this example, Google. So these global ISPs are connected together. Keep in mind, when two global ISPs are connected together, there's no customer or provider relationship between these global ISPs. And let's suppose this tier 1 ISP is connected to, let's suppose this is called A ISP, and this is the B ISP. So when two global ISPs are connected together, there's no provider or customer relationship between them. That is to say, A in this case does not pay to B for its services, and B does not pay to A for its services. Um, the content provider networks, in this case Google, it is connected to the global ISPs as well, and Google in this case is acting as a customer for these global ISPs. And this, let's suppose it's Taiwan, this AISP is acting as a provider for the Google. So Google is paying this AISP for its services. So these ISPs are connected together using using internet exchange points. Google is connected to these ISPs, and IXP is, with the help of IXP, we are connecting this Google with other with other global ISPs. Then we have regional ISPs. Regional ISPs are connected with each other. They can be connected to the IXPs, and they are connected to the global ISPs as well. So at this level we have the access ISPs. So an access ISP can be directly connected to the tier 1 ISP. So it can be directly connected to the tier 1 ISP. It can be connected to regional ISP, which in turn is connected to IXP, which connects them with the tier 1 ISPs. So tier 1 commercial ISPs, for example, level 3, Sprint, AT&T, NTT, national and international coverage. The content provider networks, for example, Google and Facebook, they run their own private networks that connect its data centers to internet, often bypassing tier 1 and regional ISPs. Okay, so we are done with this ISPs and the network core. Let's talk about performance. What is packet loss, and what is packet delay? Okay, so when we have the link capacity, let's suppose the link capacity of these two links is higher than the link capacity of this outbound link. So when the link capacity of these incoming links is higher than the link capacity of this outbound link, or you can think like when we have when we have these incoming packets arriving faster than those which are transmitted to this outbound link, then these incoming packets, they are stored in router buffers. So packets queue in router buffers, waiting for turn for transmission. So the queue length grows when arrival rate to link temporarily exceeds output link capacity. So we have studied about this in the last lectures as well, that um, we have the temporary memory buffers. We have the memory buffers linked with these outgoing links at each router. So these incoming packets, they won't be transmitted to this link unless the link is empty. So if there's a packet already transmitting through this link, so the incoming packets, they will get stored inside the buffer. So these incoming packets will get stored in the buffer. Sometimes when the memory of this buffer it fills up, the packet loss may occur. So packet loss occurs when memory to hold the queued packets fills up. Okay, so we have already studied about the transmission delay. The transmission delay is the delay, it's the time taken by each packet from transmitting from the source to this destination. Okay, then we have the queuing delay. The queuing delay is the time, or like the time taken by each of the packet uh, in the queuing buffers. Okay, so then we have the free available buffers. Arriving packets, they are buffered in the free space, so the packets can be dropped if no free buffers are available. Okay, so there are there are different types of delays. We have the transmission delay, we have the nodal process, we have the processing delay, we have the queuing delay, and we have the propagation delay. So let's discuss about each of these delays in detail. Okay, so as we have already discussed about the transmission delay, this delay, transmission delay is the amount of time required to push all the packets bits into the link. So it is the transmission delay is the amount of time required to transmit all of the packets bits into this link. So this is the transmission delay. Whereas the queuing delay, the packet experiences a queuing delay as it waits to be transmitted onto the link. So it is known as the queuing delay. Propagation delay is the delay, or you can say the time taken by this packet from transmitting to from source router to the destination router. And whenever a packet arrives at a router, let's suppose this is the packet which has arrived to this router. So each packet has a header attached with it. Header. So each incoming packet has a header attached with it. Those headers, the header contains the destination address, the source address, and some relevant information about the packets about the packet. So the time taken by the router in determining the destination address and the outbound link for this for a certain incoming packet, that is known as the processing delay, or the time taken by a router in determining the bit's error is known as the processing delay. So when we sum up all of these delays, we get the D nodal delay. So D nodal equals to D processing delay plus queuing delay plus transmission delay plus proper propagation delay. Okay, so processing delay is when the router checks for the time taken by the router in checking the bits errors. We will study about these various techniques of checking the bit errors later in this course, and determining the output link from the packet's headers. As typically, it is less than microseconds. So then we have the queuing delay. It is a time uh, when the packets they wait at the output link for transmission. So time taken by the packets uh, at output link for transmission. It depends on the congestion level of the router. Okay, so then we have the transmission delay. Transmission delay, we have already studied this, that the transmission delay is the function of length over R. L is the length of packets in bits, and R is the link transmission rate bits in bits per second. Whereas the propagation delay is the function of D over S. D in this case is the distance between these two routers. Let's suppose in this case, the D is the distance between these two routers. So D is the distance between these two routers, or it's the length of the physical link, and S is the propagation speed. So propagation delay is the function of D, which is the distance between two routers, and S, which is the propagation speed. Okay, so let us understand the difference between transmission delay and propagation delay with the help of this caravan analogy. Let's suppose we have a caravan of 10 cars moving on a highway which has toll booths, each separated by a distance of 100 kilometers. So we have a toll booth after every 100 kilometers. So you can think of this caravan as a packet. You can think of this whole caravan as a packet. So this whole caravan is a packet, and then you can think of, or you can assume each one of the car as a bit. So you can think of each car as a bit. So also, as you can think of this the toll service as the link transmission. Okay, so each toll booth takes 12 seconds to service a car. That is to it is you can think of this is you can assume it to be the bit transmission time. So if each toll booth, let's suppose this toll booth over here, it takes 12 seconds to service a car. So in a minute, it would take 5 cars to get serviced. So in 1 minute, we would have 5 cars to get serviced. 5 cars. Okay, so the caravan is propagating at 100 kilometers per hour. So if you remember this formula, L over R, this formula for the transmission delay. So in this analogy, if you think of if you think of this caravan as a packet, so as we have seen, since there are 10 cars in this caravan, so the length of this packet in this case, in this analogy, is 10. So if you divide 10 with 5, since R is the link transmission rate, as we have seen that the toll booth, it takes 12 seconds to service one single car, and in 1 minute it would take 5 cars to get serviced. So if we divide 10 over 5, we get 2. It means it takes 2 minutes for the toll booth to service. Um, it takes 2 minutes or 120 seconds for toll booth to service the caravan. So this is this time over here, 120 seconds, 2 minutes or 120 seconds. This is analogous to this is analogous to the transmission delay. Okay, so time to push entire caravan through toll booth onto highway. You can also find this 120 seconds by this. If you multiply 12 into, if you multiply this 12 into 10, which is the number of cars, you get 120 seconds as well. So time for last car to propagate from first to second booth, time for this last car to propagate from this booth to this booth is 1 hour. Since the caravan is propagating as 1 kilometer per hour, so 100 kilometer per hour is, which is equal to 60 minutes. So it takes 60 minutes, 60 minutes for the last car, which is this car in the caravan, from propagating from this first booth to the last booth. So the total time taken by this caravan is 62 minutes, like 2 minutes of this the 2 minutes transmission. So if you add this 120 seconds, or if you add this 2 in this 60, we get 62 minutes. So this 62 minutes is analogous to propagation delay. This 120 or 2 minutes is analogous to transmission delay, whereas the 62 minutes is analogous to propagation delay. So with the help of this analogy, with the help of this analogy, you can understand the difference between propagation delay and transmission delay. Okay, so suppose the cars are now propagating at 1000 kilometers per hour, and suppose the toll booth now takes 1 minute to service a car. So in this case, we would have the service time for a caravan greater than the time for a car to travel between toll booths. So what would happen if the toll booth service time for a caravan is greater than the time for a car to travel between the toll booths? So the question arises is, will the cars arrive to second booth before all cars serviced at first booth? So yes, after 7 minutes, first car arrives at second booth, 3 cars still at the first booth. So this situation also arises in packet switched networks. The first bits in a packet can arrive at router, while many of the remaining bits in the packets are still waiting to be transmitted by the preceding router. So with the help of these analogies, you can better understand the difference between transmission delay and the propagation delay. So this is it for today's lecture. We'll continue with the remaining topics in the upcoming videos. So thank you so very much. If you have any questions, if you have any queries, do let me know in the comments section. Also, if you have any suggestions, do let me know about them as well. Thank you so much for watching these video lectures. Do share and subscribe my YouTube channel and share these videos with your friends. Thank you so very much.